So on the back side of your 7.2 notes, we are dealing with still exponential functions, but now we're going to go into what's called continuously compounding interest. Now we deal with continually compounding interest, but technically it could be any continually compounding growth. For example, you could be talking about the growth of bacteria or multiplication of bacteria. Okay, that happens very, very rapidly. Okay, because it doesn't take bacteria very long to be mature enough to multiply, right? So therefore, they are essentially multiplying continuously. One makes two, then those two, each one of those makes two, and so on and so forth, and they just keep multiplying and multiplying and multiplying. So the growth of bacteria, the multiplication of bacteria, can be modeled as a continuously compounding event. Okay, so it's not just a monetary thing. It's not just interest that we're talking about here. Okay, it could be modeled in other ways as well. Okay, we talked about the deterioration of, what was it, the carbon-12 atom we talked about for carbon dating. Okay, that would actually be a continuously decaying function. Okay, because it doesn't just decay at the end of every day and it's like, okay, now I decayed this much. It's constantly decaying at a specified rate. Okay? But in our examples, we are probably going to talk most of the time about monetary issues, so we will use that. The first thing we need to know when we're dealing with anything that's either growing or decaying continuously is there is a new number, well, new to us, that we need to talk about. And that number is E. Okay, think E, it's a number just like pi was a number, okay? So E is the number we're talking about. And the way that they found this, it's an irrational number, and the way they found this number was by graphing this function. That function is essentially our compound interest function. Because compound interest was A equals P times 1 plus R over N raised to the NT power. And all they were doing is they were plugging everything in as 1 except for N. Okay? They were saying everything was 1. N they're changing to an X. Okay? So that's what they did. And so since N stands for the number of times a year that interest was compounded, right? All they did then is they took that function and they started plugging in larger and larger and larger values of X. Okay? What if interest was only compounded once a year? What if interest was compounded 10 times a year? What if it was compounded 100 times a year? What if it was compounded 1,000 times a year? And they, obviously these are only 4 examples, but they just kept going, kept going, kept going, kept going. Okay, what if it was compounded 1 billion times a year? 2 billion times a year? As they kept increasing the value of X, they found out that the value of Y they were getting was approximately 2.71828. And that is an irrational number, meaning it continues on. That decimal continues going. Okay? So that value, that number, 2.71828, became the asymptote of that function that they were just trying to graph. Okay? So that's where it was, I think, first discovered. Okay? That's where the number was first discovered. Since then, it's been rediscovered in many different aspects of mathematics. That's why it gets its own symbol. Okay? If you just find a number once, that's not significant at all. I could plug in X to an equation, get the number 5, and go, ooh, 5's a special number. Let's call that P. No, I can't do that. Okay? This number was found in many different aspects of mathematics. Okay? That's used a lot in trig. Okay? It's used a lot in different ways. They've discovered the value of it using different methods. Okay? So, I mean, it has come around much more, so therefore it gets its own special number, its own place in the math world. Okay? So E, and it is lowercase e, not capital E. Please make sure you write it properly. E is approximately 2.71828. So we will approximate that. If we have to approximate it, we will approximate that to 2 decimal places. So then E is approximately 2.7 2. Rounding it to 2 decimal places. So that is called the natural base. E is referred to as the natural base. So the natural base exponential functions are exponential functions where e is the base of the exponent. Again, a little refresher course. Remember, if we have b to the a power, a is the exponent, b is the base. So natural base exponential functions are where the number e is the base of the exponent. Okay? One place we're going to see this quite a bit is in our continuously compounded interest formula. I remember this formula by just remembering PERT. Okay? PERT, P-E-R-T, well, the equation is P times E raised to the RT. PERT. And it's for continuously compounded interest. All the variables still stand for the same thing as they always have for us. Capital A is the amount after a time period. Capital P stands for the principal or original amount. R is still our interest rate or growth rate, annual growth rate. And T is then our number of years, our time frame. Please remember, E is not a variable. E is a number. So, there are a couple of ways to find this on your calculators. Let's talk about calculators. For those of you watching the video, I apologize, I'm shutting you off for a moment. Okay, so now that we know how to plug in E into our calculators, let's go ahead and look at, looking at our first example here. Says, suppose we won a contest at the start of the 5th grade that deposited $3,000 in an account that pays 5% annual interest compounded continuously. That phrase right there is what tells us to use the PERT formula. Okay? If it says compounded monthly, then we still have to use our old compound interest formula. Or compounded yearly, we have to use the old compound interest formula. But if it says compounded continuously, we use PERT. Please make sure you're writing this properly. There is a level where the equation is written, and then there is the postscripts where the exponents are written. It should be written that way on your paper. Okay, it's e raised to the RT power. So, because it says compounded continuously, we're using the PERT formula. And it says, how much will you have in the account when you enter high school 4 years later? Express the answer to the nearest dollar. Anytime I'm dealing with money, though, I like to round it to the nearest penny. So that's what I'm going to do, is round it to the nearest penny. So, plugging into this, we have A equals our principal amount is the amount we started with, right? So that's going to be $3,000. We're multiplying that times E raised to the RT power. Well, what is R? Interest rate, correct? So R is that 5%, and 5% as a decimal is 0.05. And then we're multiplying that times T. T stands for our years, which is how many years? 4. So I'm going to simplify this only slightly. 3,000 times e raised to the 0.2 power. 0.05 times 4 is 0.2. So now we go to our calculators. And this has to be done with a calculator, folks. You cannot do this without a calculator. Okay? To do this without a calculator, you'd have to have old school charts and things like that we don't even have in school anymore. Because I took 0.05 times 4. Okay? So, we grab our calculator, and we want to do e to the 0.2 power. In your calculator, you should be getting 1.221402, blah, 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 blah. If people are not getting 1.22 in your calculator right now, please raise your hand. So now that we have that 1.2214 blah 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 number in our calculator, don't erase it, just push times 3,000. And so we should be getting a value of $3,664.21. Let's take a look at the next problem. If we deposit $3,500 in an account that pays 4% annual interest, again, compounded continuously, that phrase tells us to use PERT. What is the balance after 1 year? So plugging in, our principal amount is $3,500 times E raised to the RT. Well, our interest rate is 4%, so we put in 0.04. Our time frame is 1 year. So, grabbing the calculator again, we want E raised to the 0.04 power. We should all be getting 1.040 blah blah blah. Please raise your hand if you're not getting that number, 1.04 blah blah blah. Looks like we all got that. Okay, so then you just push times, don't get that number out of your calculator, simply push times 3,500. We should have $3,642.84. So $3,642.84.